So here's a video going over the Exam 3 review for our class. First, at the top of the review, just take a note of these formulas. They're only for sections 9.1 through 9.4. We don't need any formulas for 8.10 and 8.11 because that was Anova, and we are mainly using the calculator for all of that. These formulas will be provided for you on the exam, of course, but you do need to know how to find your calculator functions, like the p-value that we're using for units 9.1 through 9.4 is just like this. It's going to be the chi-square value that you found or that you find when you do your calculations. Then comma 1e99, because these are always right-tailed tests, and then your degrees of freedom. Don't forget that DF stands for degrees of freedom, and for goodness of fit, we have DF is equal to k minus 1, where k is the number of categories, but for units 9.3 and 9.4, the degrees of freedom relate to a test of independence or homogeneity, and in that case, the degrees of freedom is the number of row categories minus 1 times the number of column categories minus 1. We saw this as R minus 1 times C minus 1. And then also we have how to find expected counts. Even if you're using the calculator like I showed for unit 9.4, you still have to find the expected counts. And so we do need to remember that that is row total times column total divided by grand total. So make sure you understand how to use these formulas. Definitely use them when you're trying to practice the problems on this review sheet. So we're going to start with number 1, and I'm actually copied these problems to give myself some more space to finish them. So I'm going to go down to that part. The answer key is, of course, provided on the review sheet, but you want to try to do these problems without looking at the answer key first. So number 1, the table below shows the age and favorite type of music of 668 randomly selected people. So here we can see it's a two-way table. And we've got columns that stand for the type of music, rock, pop, and classical. And then we've got rows that give the age groups, 15 to 25, 25 to 35, and 35 to 45. Use a 5% level of significance to test the claim that age and preferred music type are independent. So right here there's a couple of key words, test and independent. So this is a test for independence. And in Chapter 9, we get some wording for our hypotheses instead of symbols. So in the first part here, we are asked to state the hypotheses. So for a test for independence, the null hypothesis symbolized by H0. In our case, it would be that our categories are independent. So in our case, it would be age and favorite type of music are independent. And then the alternative is just they aren't independent. So age and favorite music type are not independent. Something else that we notice only in this chapter, chapter 9, for the most part before this, the alternative hypothesis matched up with our claim. But in our case, the claim that age and preferred music type or favorite music type are independent, that's our null hypothesis. So I'm just going to remind myself of that by writing the word claim next to that. Because at the end, we do have to make a conclusion about our hypotheses and the claim. So we're going to need that a little bit later on. Next, are the conditions for the test met? So in our case, we do have random data. So the sample is random. And then we need to test that the expected counts are greater than 5. So here's a great example of how we can find our expected counts. So for example, we want to focus on building a two-way table that's just like the one that we have here. It's going to have 3 rows and 3 columns, and then it's going to have data that fills in those areas. So you can say rock, pop, and classical, and then you can have 15 to 25, 25 to 35, and 35 to 45. Now, for the sake of this review, it is good for you to practice making these expected counts yourself. So I'm going to do a couple just to show you this. So one thing that we do need for our expected counts are the totals, because we're going to need row totals and column totals and grand total. We know the grand total for number 1. It's the 668 that were in the sample. But we do need to find the other totals. So that's one thing that you want to do first. Find your totals, and then you can start filling in your data. So for example, in the first row, for the age group 15 to 25, you would take 50 plus 85 plus 73, and that gives you 208. And then in the second row, 68 plus 91 plus 60, that would be 219. And then for the third row, 90 plus 74 plus 77, which would be 241. And you can verify if you add up those 3 numbers that I just wrote down, the grand total is going to be 668. Now for the row totals, I don't have enough room right below, or sorry, for the column totals, I don't have enough room right below, so I'm just going to write those above just for the sake of what we have here. So for rock, it would be 50 plus 68 plus 90, which is 208. For pop, it would be 85 plus 91 plus 74, which is 250. And then for classical, it's 73 plus 60 plus 77, which is 210. And again, if you were to add up 208 plus 250 plus 210, you would get to the grand total of 668. So now, for the expected value, that would be for the column related to rock music and the row related to 15 minus 25. To get that number, what's going to go right there, I have to take the row total, which for the 15 to 25 row is 208, and then multiply by the column total, which for rock is 208, and then divide by the grand total, which is 668. So 208 times 208 divided by 668, and we get 64.766, rounding it to 3 decimal places. All right, and then we can continue into the next column, looking at pop. But still in the row for 15 to 25. In that case, I still have the row 208, but this time the column is 250, and then we divide by the grand total, which is 668. So 208 times 250 divided by 668, and that gives us 77.844. All right, so that's how we fill in the whole two-way table of expected values. So you can verify these first 2 numbers that I have here from the answer key. I do, again, recommend that you find all of those numbers by hand, by yourself, just to practice. This will be a great practice for making sure that you understand how to find these expected values. But our expected values will be these. The two that we found, 64.766, and then 77.844, and then the third entry for the first row is 65.389. The next row, 68.192. I'm just copying these from the answer key. The next one, 81.961. And the third one, 68.847. And then finally the third row, 75.042, 90.195, and then 75.763. What you can expect on the exam is I'm not going to make you fill in all of them, but I will leave some blank spaces, and you will have to find those yourself, just to make sure that we understand how those calculations work. Okay, so what I showed you on the TI 84, or 83 and 84 for the homogeneity section, section 9.4, also works with the test for independence. We can enter these values into a matrix. So what I'm actually going to do is jump over to the TI 83 app that I have, and I'm going to have matrix A be my observed counts, and then matrix B be the expected counts. And we're going to get our test statistic chi-squared from that. Once we're done with that, then I am going to do a couple of calculations just to show you how to make the chi-square by hand using the formula, but this is something that where we definitely want to use our calculator to get our chi-square value. So now, just like I showed in the other video that you can use for section 9.4, to get to your screen where you can enter numbers into a matrix, you have to push the second button and then go down a couple of buttons until you see the one that has the word matrix on it, M-A-T-R-I-X. You press that, and then you want to go to Edit, and we're going to start with matrix A. That will be the observed values, and you need to make it a 3 by 3 matrix. That's because there are 3 rows, that's the first number, and then there are 3 columns, so 3 by 3. And so you can see here I've entered in those numbers from the observed values. This is what was given in number 1. So the first row is 50, 85, 73, and then the second row is 68, 91, 60, and the third row is 90, 74, 77. If I press second and matrix again, I can then edit matrix B. Here's all the expected counts that I just wrote down. You can also verify these. We've got the first two that we calculated ourselves. That's in the first row. So there's our 2 matrices. And so then what we have to do is just run a test. We get to our tests the same way that we did before, by pushing the stat button. So I'll push the stat button. You're going to go to tests, and then down towards the bottom, just before you see Anova, which you can see here on the screen is at the bottom of this list, you see what looks like X2-test. That's chi-squared test. So I'm going to press on that. And you can see that I've already got observed is A. You have to state that on your calculator. Just make sure that you use matrix A as what's observed. When you do that on your calculator, on the chi-square test, for the observed, when it's sitting there asking you what to put in, you can press second and matrix, and then the names is what comes up, and you'll see A is highlighted first. You can then press enter, and then that shows up. And then you can do the same thing with expected. So you can do that by hand on that. Here on my app, it did it for me. I've got observed as A and expected as B. And so what you can see is that our chi-square value is 12.954 if we round that to 3 decimal places. I can also see the p-value there, 0.01 2 when I round that to 3 decimal places, and I can also see the degrees of freedom is 4 because that would be 3 minus 1 times 3 minus 1, which gives us 4. So chi squared, 12.954. P-value is 0.012, and then degrees of freedom. Again, it would be row minus 1 times column minus 1, but that's 2 times 2, and that's 4. So we've got our test statistic, that's chi squared. We've got the p-value. Now we just need to start writing some conclusions. And we start by writing conclusions about our hypotheses and then a conclusion about the claim. So how do we start by writing our hypotheses? We need to compare our p-value to the level of significance. Our level of significance is 5%. Our p-value is 1.2%, so that's less than our level of significance. So p-value is 0.012. That's less than our level of significance, which we use the symbol alpha for, which is 0.05. And so that tells us reject the null hypothesis. It also tells us that our data supports the alternative hypothesis. And then finally, now we need to reach a conclusion about the claim. How does this work? Don't try to reinvent the wheel. Just use the claim as stated in the problem. You can see I've underlined it. The claim that age and preferred music type are independent. So do we have evidence to support that? No, because we rejected the null hypothesis, which was the same as the claim. So at a 5% level of significance, there is not enough evidence to support the claim that age and preferred music type are independent. And so that's it. So let's move on to problem number 2. Problem number 2 says, a teacher figures that the final grades in the chemistry department proportions that are distributed as follows: 25% A's, 25% B's, 40% C's, 5% D's, and 5% F's. So figures that this is how the final grades in the chemistry department will fall out. At the end of a randomly selected semester, the following number of grades were recorded for 160 students. Number of A's, 42, number of B's, 36, 60 C's, 14 D's, and 8 F's. Test the claim that the grade distribution for the semester is different than what is expected, meaning this is what was observed, but what was expected was what was given before. Test at a 1% significance level, state the hypotheses, whether the conditions for the test were met, what the test statistic is, what the p-value is, and write your conclusions about the null hypothesis and the claim. Very similar directions to the previous question. All right, so first, what kind of test is this? We are essentially comparing proportions, observed proportions to expected proportions. So this is a goodness of fit test. Which is what was covered in section 9.2, essentially. So in that sense, the null hypothesis, this was stating some proportions. So proportion of A's should be 25%, or 0.25 if we write them as decimals. B's should be also 25%. C's should be 0.40, writing as a decimal. D's should be 0.05, and F's, what is expected, would be 0.05. The alternative hypothesis is just simply that the distribution that we expect here in the null hypothesis, we have a distribution that is not what is stated there. So we can say the grade distribution is not what is stated in the null hypothesis. And it essentially is just saying whatever this teacher figures the grades are going to be, it is either that or it's not. And it's what we're looking for is it significantly far away from that. You'll see that there's some symbols in the answer key. The symbol that looks like this is the Greek letter pi, which starts with a P for proportion, and then a subscript A. That just means the proportion of A's. I've just abbreviated that as A's. Okay, so there's our hypotheses. So we need to see if our conditions are met. So again, do we have a random sample? Yes. So conditions. We've got random sample. And then again, we need to check our expected values. Expected counts are greater than 5. So how do we find our expected counts in this case? Much easier than the previous problem. It's just taking the proportions from the null hypothesis and multiplying them by the total of our sample, in this case 160 students. So proportions from the null hypothesis times your sample size. That's how you find it for a test like this. And it's really just because we don't have a two-way table. We just have one row of information. So we can organize that. A's, it would be 25% of the 160 students from the semester that's in question, and that's going to be 40. B's, same thing, 25% of 160, which is also 40. C's, which would be 40% of 160, and that's 64. D's would be 5% of 160, which is 8, and then the same thing for F's. And you can verify that you got the right number of expected values by just checking that 40 plus 40 plus 64 plus 8 plus 8 adds back up to the grand total of 160, which they do. So then here, we're actually going to calculate the chi-square value by hand. So we're going to find the difference, O minus E, and then square the difference, and then divide that square by E, and then finally we can add up all of those values to get our chi-square value. So you can see a table in the answer key. You'll have a similar table provided for you, and again, it'll be just filling in some of the numbers, just like you saw on the online work. So a table that we can build, O for expected, E, and then we need to find our difference. I'm going to go ahead and just write the difference squared divided by E, which is how we saw it in the online work. And then we can add all of those up. So we'll start with the observed. And I'm just going to write these in order for the A, B, C, D, and F values. So 42, 36, 60, 14, and 8. And then the expected values that we just got, 40, 40, 64, 8, and 8. So then calculating this next row, you did this online. First, start by subtracting 42 minus 40. When you do that, you get 2. 42 minus 40 is 2. And then you're going to square that, which is 4, and then divide that by 40. So just to show you the work, 42 minus 40 squared divided by 40. 42 minus 40 is 2. This turns into 4 divided by 40. And so that gives you 0.1. So that's how you get the number that's in this row in the column that we're looking at just in this first case. So the next one would be 36 minus 40 squared divided by 40. In this case, 36 minus 40 is negative 4. Don't forget that when you square a negative times a negative is a positive. So this gives you 16 divided by 40, and 16 divided by 40 is 0.4. And then the next column over, 60 minus 64 quantity squared divided by 64. That gives me negative 4 quantity squared divided by 64, which is 16 divided by 64, and 16 divided by 64 is going to give you 0.25. So then 2 more to go. 14 minus 8 squared divided by 8. That gives me 6 squared divided by 8, or 36 divided by 8. And 36 divided by 8 is 4.5. And then finally, here we have the observed is exactly equal to the expected. And in that case, what you get is 0 divided by 8, which is 0. So then my chi-square value is the sum, that's what that symbol stands for, of all of those things that we just calculated, which would be 0.1 plus 0.4 plus 0.25 plus 4.5 plus 0. And when you add all of those up, you get 5.25. And so that's your test statistic. We need to find the p-value, which means that we need the degrees of freedom. Degrees of freedom for our case is going to be k minus 1, which k in this case stands for how many grade possibilities are there? A, B, C, D, F. 5 of them. So in this case, it's 5 minus 1, which is 4. Which means that our p-value we can now find. P-value, we're going to use chi-square CDF, and it's the test statistic value, 5.25, 1E99, and then 4. So on your calculator, go to second and vars, down to chi-square CDF, enter the numbers like we see here, 5.25, comma 1E99, comma 4, and what you get is, if you round to 3 decimal places, 0.263. So then to finish this problem, we compare our p-value to the level of significance. We then ask, are we going to reject or fail to reject the null hypothesis? And then we can make a conclusion about our claim. So in our problem, we have a 1% level of significance. So we can say that our p-value, which is 0.263, is greater than alpha, which is 0.01. So that means we fail to reject the null hypothesis. Okay, and then what does this mean about the claim? Well, the claim is what this teacher figures, which is that the grades should be distributed this way. We didn't reject the null hypothesis, which essentially means that we're not rejecting what this teacher figures. But down here we've got this first sentence. Gives us a little bit better way to explain this. Test the claim that the grade distribution for this semester is different than what is expected. That would be the alternative hypothesis. If we fail to reject the null hypothesis, that means we fail to support the alternative hypothesis. So our conclusion about the claim, I'm just going to write above here for number 2. There's not enough evidence to support the claim that, and then I'm just going to use the language of the claim. The grade distribution is different than what is expected. So that finishes number 2. So moving on to number 3, suppose that each person in a random sample of 48 male students and in a random sample of 91 female students at a particular college was classified according to gender and whether they usually or rarely eat 3 meals a day. The data from the samples were organized as follows. So we can see that we've got 2 columns, one for usually eats 3 meals a day and one for rarely eats 3 meals a day, and then 2 rows, male and female. At a 5% level of significance, test the claim that the distribution of population proportions for gender is not the same for each response. State the hypotheses, whether the conditions for the test were met, and what the test statistic is, what the p-value is, and write your conclusions about the null hypothesis and the claim. So here, this is what was covered in section 9.4. This is looking at the idea of we've got population proportions, but they're in a two-way table. So the previous problem, number 2, related to population proportions, but they weren't in a two-way table. So in this case, we're looking at what is called a test for homogeneity. And so we have some very specific hypotheses for those. You can see these in Unit 9.4. The null hypothesis is the distribution of population proportions for gender is the same for each response. Homogeneity essentially means the same. So we are testing to see if things are the same. So we can say for the null hypothesis, the distribution of the population proportions for gender is the same for each response, meaning for the response of eat 3 meals a day, usually or rarely. And then similar to the first problem, the alternative is just stating the opposite, the distribution of the population proportions for gender is not the same for each response. And also we can notice that the claim is that the distribution is not the same for each response. So I'm just going to write the word claim next to my alternative hypothesis so that that reminds me when we get to the end for our conclusions. So this is from section 9.4, which means we need to find our expected counts. And we need to verify that they're going to be greater than 5, but also we need those expected counts to make a matrix, and then we can use the two matrices in a chi-square test. So if we go up to the table that I have up above, we need to find our row and column totals. So for example, for the column usually eats 3 meals a day, 22 plus 54 is going to give me 76 for that column. And then the next column, 26 plus 37 is going to give me 63. And then for my rows, 22 plus 26 is going to give me 48. And then 54 plus 37 is going to give me 91, which we do know because that was given to us. And then finally our grand total, which would be 48 plus 91, 139. So our expected counts, remember row total times column total divided by grand total. We're just going to have 2 rows and 2 columns. So for example, in the space that would be male and usually eats 3 meals a day, it would be row total of 48 times the column total of 76 divided by the grand total 139. 48 times 76 divided by 139, and we get 26.245. Keeping in the same row, I would take the row total of 48, multiply by the column total for rarely eats 3 meals a day, which is 63, and then divide by the grand total, 139. 48 times 63 divided by 139, and that gives me 21.755. So this is just like problem number 1, only there's a few less entries to put in. So if we go to the row for female, we would have 91 times 76 divided by 139, and that would give us 49.755. And then finally, for the last entry, 91 times 63 divided by 139, and that would give us 41.245. So now that we've got our expected and our observed counts, we can go over to our TI-83 or 84 and create a new matrix to then calculate our chi-square value. So let's go take a look at that. Okay, so I'm back here on my calculator, again to get to my matrices, as in the plural of matrix, second, and then A couple buttons down where you see matrix, press that. I need to go to edit, and then I select A. It's a good habit to stick with your observed values as matrix A. And I've entered those in here. These are what was given to us in problem number 3. First row is 22, 26. Second row is 54 and 37. And then for my expected values, second and matrix, edit, and go to matrix B, then here's the expected counts that we just calculated for problem number 3. First row is 26.245, next one 21.755, next one 49.755, and then the last one 41.245. You can actually see here they're using the unrounded values. Okay, so now we just run our test. So you can press stat, go to tests, and then go to chi-square test. And then let me show you how you can actually enter those matrices for you. So when I press that, it automatically assumes that my observed is A and my expected is B. So how do you make that little symbol with the square brackets and A show up and then the square brackets and B show up? Very simple. When it's asking you to input something for the observed, from that screen you can press second and matrix, and then on this screen you have names selected. You'll see that the first one that has A is highlighted. Press enter on that and you'll get this symbol, the square brackets with an A. And then when you go down to expected, you could do the same thing. Second, matrix, and then push down on your direction button so that B is highlighted and press enter, and then you'll see that symbol show up. That's how you get those two symbols down there. And then press enter to calculate. That's what you want for the test statistic. So for me, I can see on the bottom right, chi-squared equals 2.314 if we round that to 3 decimal places. P-value is 0.128, and then of course you can see that the degrees of freedom is 1. Because you have 2 rows and 2 columns, that gives you 1 times 1, which is 1. So our results, chi-square equals 2.314, p-value equals 0.128, and then degrees of freedom, again, it would be 2 minus 1, number of rows minus 1, times 2 minus 1, number of columns minus 1, which is 1 times 1, or 1. And so then finally we compare our p-value to alpha. Our value for alpha was 5%. That's our significance level. And our p-value is greater than that. So what does that mean? If it's greater than our level of significance, then we fail to reject the null hypothesis. And this also means the data does not support the alternative hypothesis. Once you have those two understood, that then helps you understand how to write a conclusion about your claim, because I reminded myself that my claim was the alternative hypothesis. If I just said that the data doesn't support the alternative hypothesis, that means the data does not support the claim, and you've already started writing the conclusion. The data does not support the claim. And then, what was the claim? That the distribution of population proportions for gender is not the same for each response. These three problems, 1, 2, and 3, really do summarize everything from Chapter 9. There isn't anything else besides this, and we can see how the formulas are used, and then also just the calculator function of either finding p-value with the chi-square CDF or finding your chi-square value using the chi-square test. So then finally number 4, which is a review of Anova, units 8.10 and 8.11. A manager would like to determine if there are significant differences in the mean sales among 4 stores. The following table shows the sales in thousands of dollars tracked over 5 days. Test your claim using a significance level of 5%. The way that we know that this is Anova is because we aren't looking at proportions. We are looking at differences in the mean sales. So that then tells us how to write our hypotheses. We have to use the symbol for mean, which would be mu, but then we have 4 stores, 1, 2, 3, 4, that will all have an average sale that goes over these 5 days. So we have mu1, the mean of the Alhambra store, is equal to mu2, the mean sales of the Burbank store, is equal to mu3, which is the mean sales of the Cerritos store, and then equal to mu4, which is the mean sales of the Downey store. And then the alternative hypothesis is just simply at least one of those population means is different from the other. So at least one population mean is different from the others. Okay, so now this is a very simple problem to answer because we are just going to use the Anova test. The one thing that you definitely have to remember is that we are going to use lists and not a matrix. And one other thing that you want to keep in mind is that your lists, each list should be relative to each store. So while it looks like I have 5 columns of data here, I'm going to be entering into each list the same way that I have my numbers here. I've got 4 stores. So list 1 is going to be all of the data from the first store. List 2 is going to be all of the data from the second store, and so forth. Okay, so keep that in mind. Just because it's presented to you here as columns, we aren't looking at something related to each day. We're looking at something related to each store. And there are 4 stores, so there should be 4 lists. So back on my calculator, how do you get to the lists? You have to press Stat, and then Edit, and then here I've got L1. And you can see L1 is all of the data from the first store, 10, 15, 10, 20, and then 20. L2 is all the data from the second store, 20, 20, 25, 15, 20. L3 is all the data from the third store, 3, 7, 5. Oh, that should be a 10, not a 1. And then a 4. And then finally, list 4 is all the data from the fourth store, 30, 25, 30, 35, and 30. So now how do I run my Anova test? You get to your tests the same way we have before. Press the Stat button, go to Tests. Anova is all the way at the bottom. And then you just need to type in your lists by name. So second and 1 is L1, comma, second and 2 is L2, comma, second and 3 is L3, comma, second and 4 is L4. And then press Enter. And here you can see the same information that you can verify with the answer key for this problem. We've got F, which is our test statistic. That's 35.295. The p-value, that's the lowercase p that's sitting there, 2.76652. But don't forget, look all the way at the right, and you'll see there's an E -7. So let's go write that down. Our test statistic, that's F. That was 35.295 when we rounded 3 decimal places. The p-value, you can see that comes from your calculator, p equal 2.767, but you cannot forget about the e with the negative 7. Why? Because that means you get a 0 point and then 6 zeros. It's one less than the number. And then finally the 2767. Remember, your p-values have to be smaller than 1. So you can't have something like 2.767. So you got to remember how that e negative 7 part works. Now that's a very small p-value. That is less than the level of significance. So the p-value is less than the level of significance, which we call alpha. What does that mean? Reject the null hypothesis, which also means you've got data that supports the alternative hypothesis. And so then, what is the claim that we were testing? A manager would like to determine if there are significant differences in the mean. That's the claim. Do we have significant differences? Yes, because we have data that supports the alternative hypothesis, which says that at least one population mean is different from the others. You could probably tell just by looking at the data which store has significantly different sales over these 5 days. So our conclusion, the data, we can say, suggests, as an alternative way of writing this, data suggests that at least one store has a mean sales that is different from the others.